This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Sure.
So here I see this modular, and I still wonder how like X and Y is 8 bits, but here it's actually 9 bits now.
Correct, because if you add two 8-bit numbers, it might overflow to get a 9-bit number.
So this one will recognize it automatically, so I don't have to assign extra, like say, full adder and half adder.
Correct, it'll do it all for you.
I'm thinking, so because this one will not do until the time delay, and here's two display actually, so it will print the same thing twice. Okay. Thank you.
No. Starting time. Welcome everyone to lecture 11. And today we get to have a little bit of creativity. So I showed you how to implement this finite state machine using a very standard procedure. Today we're going to implement it using a bit of human intelligence. So finally, an opportunity to exercise some creativity here. It will still be a finite state machine. It will still do exactly the same job, but it will have a different state diagram. So it's possible for two finite state machines to have very different state diagrams, but to have the same input-output map. So for those that are interested in these things, you really want to think of the input, the internal state, and the output. And it's possible to have very different internal states, but end up with the same input-to-output map. In other courses, if you're to do control theory or signal processing, you've got state space models. The state is the internal state, the same as in here. You can have different state space models, different internal representations that actually behave externally in exactly the same way. As I keep saying throughout the course, the reason why we care about different implementations of the same specification is that different implementations will have different advantages and disadvantages. You need to think of the cost to develop it, the cost to modify it, the cost to implement it, the power it uses, all these factors. So just being able to do one thing in one way is not good enough for a senior engineer. You need to be able to do one thing in 10 different ways. So although this course started with some formulae, for combinational circuits we go from truth table to sum of products to implementation, or better in this course, we go from truth table to let Quartus figure it out and implement it for us. And then we looked at the behaviour to the state diagram to a standard way of implementing a finite state machine. Well, today we're going to be creative. We're going to think algorithmically, think like engineers, and work out how to implement this finite state machine in a very different way. Before I do that, we need to understand shift registers again. I've mentioned these before. Unfortunately, I managed to misplace my stylus. I will attempt to draw with my finger and see how it goes. So if I want a shift register, then remember, if you use microcontrollers or program in assembly language, a shift register simply, I have got a register here, and it starts off with some bits in there, say 101, and I can shift to the left or shift to the right, doesn't really matter. If I'm going to be shifting to the left today, so if that's the current value of my shift register, so a register is just like a variable. So my variable contains 101, or if you prefer decimal, that's the number 5. If I shift 1 into that to the left, you think of that as saying, I'm going to take the number 1 and I'm going to shift it in there, and just like the three little whatevers in bed and they all roll over, what's going to happen is that this one here is going to drop out onto the floor and gone forever. The 0 is going to shift over, and so I'll have 0 here. This 1 is going to shift over, so I'll have a 1 here, and this 1 I'm shifting in comes in here. So all the shift register does is when you tell it to shift left, everything moves over one place to the left, and the new number comes in to bit 0 in this case. Any questions about shift registers? So these are very easy to implement using flip-flops. If I want to implement this, then I simply need to have 3 flip-flops where the input's on the left, the output's on the right. That's by convention, and I've got my clock here. I'm only going to draw 2, sorry, because my finger's getting tired. But imagine I have 3 flip-flops there. You simply connect the output of one to the input of the next one. Now this is going in the opposite direction by convention. My shift register over here is shifting to the left. The way I've drawn my flip-flops, they're shifting to the right, but hopefully you can adjust to that. So if I had 1 0 here inside my flip-flops, meaning 1 0 is coming out, then at the rising edge of the clock, this 0 disappears. This 1 at the output of the first flip-flop gets photographed by the second flip-flop, so this one shifts across to here at a rising edge of the clock. And whatever number I have coming in here, say it's a 0, that gets photographed and that gets shifted across into here. So I can make a shift register out of flip-flops very easily. Any questions about shift registers? As usual, in Quartus, I can create this even more easily than by this drawing here. I can just do it mathematically, as we'll see presently, in a very simple way. But this is what's actually going to be implemented. We'll get to the Verilog implementation soon. Now, what do I want? Let me go back to my finite state machine. And remember, its job was to detect either 4 zeros or 4 ones in the input stream. From the state diagram we were given, we could work out that was its job in life, to find 4 zeros or 4 ones. Whenever it finds 4 zeros or 4 ones, it outputs a 1. If the current and the previous 3 inputs are not 4 zeros or 4 ones, the output's a 0. That's its job. So how can I implement this same functionality but not using that state diagram that we showed before? Well, as soon as we start to think in terms of shift registers, then all we need to do is have a shift register that remembers the last 4 inputs. Because the output is just a function of the last 4 inputs. If the last 4 inputs are all 0, the output is a... If the last 4 inputs are all a 1, the output is a... And if the last 4 inputs are anything other than all 0 or 1, the output is a 0. So all I need is to have a shift register to remember the last 4 inputs. Well, there's a small caveat that we'll get to. I actually need 2 of them, but basically that's all I need. So any questions about this slide or the key principle? We just want to remember the last 4 inputs, and then we can test. Are they all 0 or all 1? If they are, output a 1, otherwise output a 0. And this is also a finite state machine, and it will also do the job that we want. As with many things, any creative endeavour, you get a good idea, you move forwards, then you realise, oh, there's a little bit of a trick here. But often you can fix up that trick. In this case, the trick is if I've got a shift register, how do I initialise it? Well, if I initialise my shift register to all zeros, the obvious choice, I'll immediately get a 1 coming out of my machine, because it'll say I've detected 4 zeros. And if I initialise it to all 1s, I'll have the same problem. So, okay, maybe I initialise it to 0101, but then I have a subtle problem. If I initialize it to 0101, then I've got a 1 here at bit 0. If I now have 3 ones at the input, my shift register will end up being 4 ones. And it will prematurely detect that there were 4 ones when in fact there are only 3. So bit 0 of the shift register, it needs to be initialized to a 0 if I'm trying to detect 4 ones, and it needs to be initialized to a 1 if I'm trying to detect 4 zeros. So I have a problem. I can't do this with a single shift register, but I can do it with 2 shift registers, because it's the initialization that's a little bit tricky. Any questions there? That's on the slide, so you can think about it at home. Yep. If we were just living in model sim world, that would work perfectly. But I'm thinking about how to implement this in hardware, and I can't get an X into my flip-flop. So good thinking, it will work in model sim, but not on inside your FPGA. So the flip-flops in your FPGA are either 0 or 1 at the output. But nice thinking. Any other questions? Okay. So in those 2 slides I've basically said what I said here. It might require you to think a little bit and play around with a piece of paper, but that's why we need 2 shift registers. So the next question is, how do I implement a shift register? Well, option 0 would be, I showed you, I just need to get a bunch of flip-flops and connect them up. You could in principle declare a module D flip-flop, and you could in principle wire them up, bang, bang, bang. That's the slow way, but that would work. So that was option 0. Option 1, which is what I like, I just have this line of code here. Always at pos edge clock, that gives me a flip-flop, because the only time SR changes is inside this loop here. The only time SR changes is at the rising edge of the clock, therefore SR must be a flip-flop. In this case, SR has got 4 bits, so in fact I get 4 flip-flops in parallel. And what's on the right-hand side is the input to my flip-flops. And the input simply says, well, whatever the current value of my flip-flops are, so pretend SR is currently equal to 0101. So if SR is currently 0101, and imagine that in is equal to 0, then what is the right-hand side of this guy going to be? Well, the curly brackets mean concatenation, remember, so I'm going to be forming a 4-bit number out of a 3-bit number and a 1-bit number. The 3-bit number SR2 to 0 is going to be this part of SR. So therefore, this front half of this guy here is going to be 101, SR2 to 0. And then the last bit here, in, I said in was 0, so I'm going to get this. So if SR was equal to 0101 and in was equal to 0, then after the rising edge of the clock, SR is going to be 1010, which is exactly what I want of the shift register. It's shifting, yes, it's shifting to the left. So given this, when I shift to the left, the highest bit drops off and it gets joined by the smallest bit there. So this is, to me, is the nicest way of implementing a shift register using basic Verilog operations. Any questions? If you are a C fanatic, programming Arduinos and the old-fashioned Z80s and everything, you would recognise option 2 as your first choice. But that's only for people that like microcontrollers and whatever. So this makes sense pretty much in C code, at least this line does here, minus the non-blocking assignment. So two less than signs in a row means shift to the left the number of bits given after it. So SR less than 1 means shift SR to the left by 1 bit. This works in C. You can try it out in your favourite C compiler. Once I've shifted it to the right by 1 bit, I then need to stick into bit 0. Now once I've shifted it to the right, by definition we know that that has introduced a 0. If you just do a shift, sorry did I say to the right? When you do a shift to the left, when you do a shift in C, the incoming digit is going to be a 0. So I'm going to have 0 in bit 0. If I want bit 0 to become what in is equal to, the trick is to OR it within. I know that the current number is 0, so if in is 0, 0 or 0 is 0, it stays 0, that's correct. And if in is 1, I have 0 or 1, which is 1, and that's what I want too. So this trick will also do the job. But you save that for when you're programming microcontrollers. This is, I think, the clearer way of doing it in Verilog. Any questions? So now this code here, and if you recall from last lecture, my finite state machine was quite long because I had a case statement there with about 9 cases or whatever. Now my finite state machine is just a few lines of code, and it does exactly the same job. I have 2 shift registers. One of them I use to detect 4 zeros. One of them I use to detect 4 ones. Why? Because you have to think about how to initialize these registers and to eliminate the possibility of declaring there were 4 zeros when in fact there are only 3 zeros and you initialized it with 0 in bit 0. And the same for the other one. So if I want to detect 4 zeros, then I initialize my shift register with anything I like ending with a 1 here. So why not all 1s? And here if I want to detect 4 1s, I have to initialize my shift register with a number ending in 0, so why not 4 zeros? This implements 2 shift registers. It's just the same code as before, repeated twice. So I've got 2 shift registers. And the output logic is really simple. As we said at the start of today's lecture, the output's going to be a 1 if either my first shift register has detected 4 zeros, or if my second shift register has detected 4 1s. And that's it. So, given the problem specification, I could have written this code in 30 seconds, or I could have drawn a state diagram and done it that way in about 5 minutes. So sometimes there are benefits to being creative. Any questions so far? So it does the same job as what our finite state machine did on Monday, but using a very different internal state representation. We're not following that state diagram at all, and I'll discuss that presently. I am claiming it's a finite state machine. I can always make that claim in this course because the only thing you can implement is a finite state machine, and also everything is a finite state machine. So unless you're being pedantic, and if I just have combinational logic, then you can argue over pedantics whether that's a finite state machine because it's a trivial one because there's no memory here. But that aside, everything's a finite state machine, which means we need to be able to understand this in that block diagram. So every finite state machine has got flip-flops here, the current state at the output logic that takes the current state to the output, and that feedback loop that takes the current state, puts it through some logic together with the input to get the next state logic. That is the canonical representation for a finite state machine. And if this guy here is a finite state machine, you must be able to put it into that canonical form. Hence I ask you, what is the state, what is the transition logic, and what is the output logic? Who would like to have a go? What is the state of this finite state machine? How is it represented? Where is it stored? What's its life? Perfect. The state is stored in SR0 and SR1. That is our internal memory. Those are our flip-flops. Perfect answer. Any questions about why that's the state? I'll have it up again on the next slide so you can ask a bit later. So in a finite state machine, you ask yourself, where's the memory? Where are the flip-flops? And that tells you the state. In this case, SR0, SR1, they are our flip-flops, therefore they are our state. What is the transition logic? So transition logic I also call next state logic. It tells me what my next state is, given the current state and the current input. Where is the transition logic hiding in this Verilog code? Oh, I can't say no, but I'm sort of claiming that half of this is my state. So I actually prefer a more specific answer. It is hiding in here, but which part of this would you call specifically the transition logic? So I've been a bit naughty here. I have combined two things in one. If I was being more explicit, I would declare some wires. I would explicitly write down the transition logic, and then for my flip-flop code, I just have SR0 takes the value of next SR0. But I've combined two things into one. Exactly. So on the right-hand side, this equation here, these two equations here, that is exactly where my transition logic is. That's the combinational circuit that takes the current state and the input and produces the next state. Well done, guys. Any questions? And then, dare I say it, the output logic should be the easiest one to spot. What is the output logic here? The output logic for more finite state machines determines the output based on the current state. And that's it. Yep. Because, okay, I'll give you two answers. When we implement this in hardware, and that's the best way of thinking about it, then this just becomes some logic gates. And the logic gates simply have got the current state on the left-hand side and the output on the right. And whenever the state changes, that goes through the logic gates and gives you an answer. So this is always running in hardware. It never stops. When we simulate it, we want to try to simulate exactly the same thing. That's why Model Sim simulates everything in parallel. So this assign block is always running. We said in an early lecture that as soon as you have an assign, you grab a friend and say, please friend, watch for SR0 and watch for SR1, and whenever they change, redo this computation. So in Model Sim, this is always running as well. As soon as this or this change, that will change. In hardware, because there's a logic gate there, in model sim because your friend is waiting for them to change, and that will change that, as we discussed earlier on. Any other questions? Okay, so I think I summarised this on the next slide. Oh no, I have a detour first, but I do summarise that eventually. So I'm now deriving it for you. You got the right answer. When we did our first implementation, we had 9 states, and therefore we used 4 flip-flops. So in our first implementation, our state was 4 bits. Here, my state is 8 bits, and it's not one hot encoding. It's something else again. By choosing it in this way, the transition logic is very, very simple. That's why I didn't need a case statement for the transition logic. Before I had a case statement with 9 or so cases. Here my transition logic is simply implementing 2 shift registers, which I can do algorithmically. The transition logic, you work that out too, is just that, and that's the reason why. And the output logic, you got that one too. So I'm going to move on, and here's the summary. I've tried to colour different things in different colours and remind you of this basic block here. Now every time I look at that block I get a headache because there are letters everywhere, but I just think to myself, I've got my memory here. The output of the memory, the output of the flip-flops is my current state. The current state goes through the output logic to give me the output, that makes sense. And the current state goes through this transition logic together with the input to give me the next state. And that's it. So to me it's easy to think like that, but I get a headache looking at that diagram which I cut and paste from somewhere because it's got symbols everywhere. So just break it down, and it's as simple as 3 parts. Your memory, your output, and the next state. That's all it is. Any questions so far? So what I would like you to do for homework, because it's a good exercise in drawing state diagrams, which, well, in theory there'd be 100% probability you'll have to draw a state diagram in the test and in the exam, except that they are a nightmare to mark because students can make very creative mistakes. So you don't always have to draw one because of that reason. But you should definitely be able to draw state diagrams, so it's very good practice to, given this finite state machine, explicitly draw the state diagram for it. That's your homework. If you get stuck, ask on the discussion board. You may wish to compare the 2 state diagrams. Our first implementation, which is based on this one over here, and our shift register implementation, and you'll find that our shift register implementation actually has more states. In one sense, it is less efficient because it's got more states than it has to. But we have a saving there. By having more states, we've simplified the transition logic greatly. So there's no clear-cut winner in designs. Often there's a trade-off. So what we have shown is that, so firstly, what do I mean by an equivalent state diagram? If I take a state diagram, and remember a state diagram is a bunch of circles, a bunch of lines connecting the circles. Inside each circle you give it a name. This state is Fred, that state's Charlie. And you tell me the output given the state I'm in. If I'm in state Fred, the output might be 23. If I'm in state Charlie, the output might be 56. And for the lines coming out of each circle, for every possible input, you have to tell me which state I go to next. It's okay to go to the same state, but for every possible input, you have to tell me the transition. Once you've done that, and you've told me which state I start in, you've given me a state diagram. That's all a state diagram is. Now, given a state diagram, if you go in to the state called Fred and change the name to Freddie, well, you haven't really changed the state diagram. Pedantically, you've changed it. Technically, you haven't made much difference. If you just change the names, then we call them equivalent state diagrams. You haven't made a substantial change. A non-equivalent state diagram is a state diagram which it doesn't matter how much you rearrange it and change the names, you can't make it the same as the other one. So what we've shown that our two implementations, implementation on Monday and the shift register implementation, they are definitely different state diagrams. They are not equivalent. To start off with, they have a different number of states. So changing the names of the states can't make them the same. So we have shown that very different state diagrams can have exactly the same external behaviour. And this accords with state space models that you may have learnt about in control theory and signal processing, etc. Going in the opposite direction, that suggests, given a state diagram, there might be ways of simplifying it. Or there are, but they're not part of this course. I just want you to be aware of that. So, let me just double check. Yep, that concludes today's lecture, unless there are any questions. Happy to take questions now, happy to take questions after the lecture. I did say things would slow down a little bit after the first 10 or so lectures to get you up to speed. But on the other hand, you've got a fair bit to think about. So just because the lecture's short doesn't mean you don't have things to think about that may take time. Any questions? Okay, thank you.